The next video in our Tools of Chemistry unit is on accuracy, precision, and error. Looking at our standards and learning targets here, we are still working on applying our understanding of uncertainty in measurements. And this video will focus on two of the remaining learning targets here. The first one you see listed here, differentiate between accuracy and precision, is as we will learn, they will not the same thing. And we want to be able to calculate the percent error of a measured value. So jumping in here, the difference between accuracy and precision. So just a couple of definitions here for the two. First of all, accuracy and precision, they are not the same. We might use those two words interchangeably in our everyday language, although probably we use the word accurate or accuracy more often than precision or precise. Accuracy, or if a measurement is accurate, that probably has the meaning you basically think it does. Accuracy refers to how close measurements are to the accepted value, or what we might consider to be the right answer. So when you say a measurement is accurate, that means it is close to the accepted value, or again what we might say is the right answer. Precision refers to how well a series of measurements agree with one another. In other words, the consistency of those measurements. Are they close to each other? It has nothing to do with how close they are to the right answer. In fact, measurements can be very precise, but not accurate at all. A very good graphic to help us understand the difference between accuracy and precision would be looking at a target. So for example, if you were shooting an arrow or shooting a bullet or something at a target and a series of arrows, not just one, but a series of arrows, a series of bullets, then we would have a look at something like this, where if we were all over the place, hardly any of our shots were on the bullseye, we were not very accurate. Not only that, but the shots are far away from each other, meaning we're not precise either. In the second picture here, you can see we have very high precision. Our measurements or our shots are very close to each other, so they are precise, but they're not very close to the target, or at least the bullseye, so that would be very low accuracy. In the next example here, we have fairly high accuracy, meaning our shots are close to the bullseye, but they're not particularly close to each other. So we would say that's high accuracy but low precision. In measurements, typically that just means we're lucky. If we're not very precise, typically that means we're not going to be very accurate either. This is more luck than anything else. And then finally, in the last picture here, this is the ultimate goal. Whether we're at a shooting range or we're measuring in the chemistry lab, we want both high accuracy and high precision. This would come from using proper technique every single time. You are not able to have a high level of precision nor a high level of accuracy if you're not using correct technique, whether we're talking about shooting a bow and arrow or measuring with a graduated cylinder or thermometer or anything else. You're not able to have that good accuracy and precision if you're not using proper technique all the time. So let's look at an example of how this applies to data. So let's say we had two students and they measure the density of some unknown metal 3 times each, and they get the following data. So you can see student 1 measurements here. Student 1 gets these density values. Student 2 gets these density values for this metal. Let's say that the accepted value for the density of the metal is 7.08 grams per centimeter cubed. In other words, if you went and looked up the density of this metal in some sort of reference, or maybe you looked it up online, this is the value you would see. So in other words, that is what we might consider to be the right answer. So which student was more accurate? Look at that data and tell me which student was more accurate. Well, hopefully, thinking about what the definition of accuracy is, how close to the accepted value a measurement is, that is student 2. Student 2 is more accurate because student 2's data are closer to the accepted value. Now, on the other hand, which student was more precise? How do you know? Well, looking at the data, we can see that student 1's data is closer to each other. There's not as much of a range between the high and the low. There is more consistency there. So student 1 was more precise because student 1's data are more consistent. So we have looked at the difference between accuracy and precision. We can now differentiate between those. Now let's look at how we do some calculations along these same lines. So there are really two calculations that we want to be able to do. Those are error and percent error. Error is simply the difference between the measured value and the accepted value. So we take whatever you had as your measurement in the lab, and you subtract the accepted value. Note this could be positive or negative, which makes sense because your measurement can be high or low. If your measurement is larger than the accepted value, meaning measured value is going to be greater than the accepted value, this error will be positive. If your measured value is lower than the accepted value, then the error will be negative, which makes sense, I think. If your measurement was too low, then the error is negative. The percent error, that is the percentage of the accepted value that the error takes up. So what we do there is we simply take the error, that's what you calculate up here. You take the error, the difference between the measured and the accepted value, you divide by that accepted value, and then you multiply by 100 to turn that into a percentage. And that is your percent error. And just like error, percent error can also be positive or negative because your error could be too large, or your measured value could be too high, or could be too low. So let's look at how we use those calculations in an example. So let's say you measure the length of a wood block to be 28.65 centimeters. The actual length of the block is 29.94 centimeters. Determine your error in percent error. So error, we take the measured value minus the accepted value. Well, here your measured value is 28.65 centimeters. We subtract the 29.94 centimeters, and your error is a negative 1.29 centimeters. The fact that your error is negative means that your measured value was too low. Now note, I hope you can measure better than this, because if you're off by over 1 whole centimeter when the measurement's less than 30, then that probably means we don't know how to use a ruler very well. But that's beside the point. Alright, so now that we have our error, let's calculate our percent error. So all we do is we take the error divided by the accepted value. So our error from before was negative 1.29 centimeters. We divide by the accepted value of 29.94 centimeters, and to turn that into a percentage, we multiply by 100. And note your units here will cancel. Centimeters divided by centimeters gives you nothing, but then it is a percentage because it's out of 100 because we multiplied by 100, and this would give you negative 4.31%. Notice your sig figs here on these calculations. On the error calculation, we're following our addition subtraction rules. Both of these values have a sig fig to the hundredths place, so our error goes to the hundredths place. In the percent error calculation, it's a division, so we're looking at number of sig figs. I have 3 sig figs here in the error, 4 in the accepted value, so I can keep 3. So there's my 3 sig figs, the 4.31%. Alright, again, same idea here. This is the same data you saw before in the example of the difference between accuracy and precision. And again, we're given the accepted value of 7.08 grams per centimeter cubed. But now we're asked to calculate the error and percent error for student 1. Now you might be wondering, how do we do this if there's multiple pieces of data here? Well, the easiest thing to do is simply to calculate the average first. If we have a series of measurements measuring the same thing, we'll calculate the average for student 1 first, and then we'll use that value as the measured value. So to calculate average, as you know, we'll just divide the sum of the numbers by the number of numbers. And then when you do that, as far as your sig figs are concerned, the sig fig rules here would be just looking at decimal places, precision because it's addition. You might say, but it's division too. But here's the thing though, this division is not by a measured value. It's by exactly 3. So when we calculate the average, we're going to keep our average to the hundredths place because that's what the measured values go to, each of them. So our average of student 1's data is 6.32 grams per centimeter cubed. So now we'll use that to find the error and the percent error. So to find the error, again, just the measured value minus the accepted value. So our measured value is 6.32 grams per centimeter cubed minus the 7.08 grams per centimeter cubed, and we'll have an error of negative 0.76 grams per centimeter cubed. Again, notice it's negative because the measured value was lower than the accepted value. Now to find the percent error, we take that error divided by the accepted value from above, the 7.08 grams per centimeter cubed, and this will give you negative 11%. Again, notice your sig figs here. In the subtraction for the error calculation, we're looking at the precision, or in other words, the number of decimal places, and both of those go to the hundredths place. And so we keep our answer to the hundredths place. Here in the error calculation, the percent error calculation, it's division. So we're looking at number of sig figs. We have 2 sig figs in the error, 3 in the accepted value, so I get to keep 2. So that will round to the negative 11%. All right, here's a practice problem for you to try on your own. You can read it and then pause the video, see how you did, and you can make any corrections as necessary. Alright, so in this experiment you have measured the melting point and you obtained those 3 values there, the 56.7, 58.1, and 53.9 degrees Celsius. You're given the accepted value and you're asked to calculate the average of the 3 trials, the error, and the percent error. So to find the average, again, it's the sum of the numbers divided by the number of the numbers, and then you'll round that to the same precision as you had with the measurement, so round it to 1/10 of a degree Celsius. That should give you 56.2 degrees Celsius. To find the error, then, we'll take that measured value and we'll subtract the accepted value. So 56.2 degrees Celsius minus 55.2 degrees Celsius. And notice your error is now positive because your measured value is greater than the accepted value. Also notice the sig figs here. Both the measured and the accepted value have a sig fig in the tenths place, so our error should go to the tenths place. So if you would simply write 1 degree Celsius, that would not be correct. It is 1.0 because we should have a sig fig there in the tenths place. So our error is 1.0 degrees Celsius. We will now calculate our percent error by dividing the error by the accepted value. So 1.0 degrees Celsius divided by 55.2 degrees Celsius, and multiplying by 100 to turn that into percentage, that will give you a percent error of 1.8%. Alright, finally here, you might be wondering why we have to calculate both an error and a percent error. Why can't I just do an error and call it good? Because that tells us how much we're off by. Well, here's a good example to help you understand why. Let's say you measure a length of your book to be 28.00 centimeters. The actual length is 32 centimeters. Your error here is negative 4.00 centimeters because you are 4.00 centimeters too short. And then if you calculate the percent error, if you take that divided by the accepted value multiplied by 100, you're off by 12.5%. Okay. Now let's say we also measure the length of a football field, and our measurement is 10,968.80 centimeters. The actual length is 10,972.80 centimeters. You'll notice here your error is also 4 centimeters too small, or negative 4.00 centimeters. So the error here is exactly the same as in measuring the book. But this measurement is way, way, way better than the book measurement, because here your percent error is only a negative 0.0365%. Because that 4 centimeters is a tiny, tiny percentage of the overall measurement. Whereas if you're 4 centimeters off measuring the length of a 32 centimeter book, you must be blind. That's really the only way of putting it. That, or you don't know how to use the meter stick or the ruler, whatever you're measuring, something along those lines. But if you're only 4 centimeters off measuring the length of a football field, that's pretty darn good. So we can see here that error and percent error, while they do in essence measure the same thing, they are not the same measurement. They don't communicate the same information. In other words, what we're saying here is error is relative. If you can have the same error, but it could be an excellent measurement or it could be a really bad measurement, depending on what the total value of the measurement is supposed to be. All right, so we've looked at how we differentiate between accuracy and precision. We've also looked at how we calculate the error and percent error of a measured value.